think everything is fine. Okay, good morning, everyone. Welcome to the Computer Architectures and also Processing Systems second module, Computer Architectures course. My name is Sinan Yıldırım. You can basically call me Sinan. Sinan is fine. I am an associate professor at the Department of Information Engineering and Computer Science. I do research in embedded systems and computer architectures in general. So I teach computer architectures this semester. For the third year, I teach embedded software for the Internet of Things course. And also I have a master's degree course, which is low power embedded systems. As you see, I do a lot of embedded systems related work. Basically, I am very familiar with the topic, computer architectures. So it is also always nice to have the lecture from someone who is also interested in the field. Basically, my office is 120 in Powell 2. If you want to reach me, obviously it is the point. First of all, I would like to give a kind of brief overview of the course, what we are going to see all together. Actually, this is like a course for the first year in Informatica or computer science students, right? And also it's a course for the second year for EHS students. Basically, EHS students are a bit more familiar with some topics that I am going to teach, but it doesn't mean that it will be a disadvantage for computer science students. So everything you need, we will be covering during the lectures, so don't worry. This is a theoretical course. We will have theory lessons, lectures. Obviously, this year I will try to incorporate some practical, maybe assignments, if possible. It depends on my time and also the availability of the tutor of the course. And also, as you know, like we have 48 hours of teaching. We have 12 weeks. Each week we have 4 hours, 2 lessons each, 2 hours. In total, we will see each other 4 hours, good or bad, I don't know. You will see in the end of the semester, right? And our lectures is scheduled for today in the morning, and we have a lecture on Wednesday, but maybe we might move it to Tuesday if there is feasibility. I will check because I have some conflicts, but for now this is the schedule, right? Monday and Wednesday. It's correct, right? Wednesday time is also. I didn't do a mistake here from 1:30 to 3:30. So, what are we going to explore? First of all, this course is, let's say, logically divided into 3 parts. The first part is dealing with computer arithmetic, some basic, let's say, logic, digital design related topics will be covered in the first, let's say, part of the lecture, which will take roughly 2 weeks. And then we will start exploring instruction set architecture, which is the assembly language. We will see, basically 3 assembly languages. One is RISC-V, and the other 2 will be Intel and ARM. These are very common instruction set architectures that are, let's say, that have different characteristics, different specifications. We will all see all these things, and you will be very familiar with assembly language, very low level, let's say, a language that is directly understood by the computer, I would say. And the third part will be dedicated to architecture level concepts. For example, we will deal with like how a CPU looks like from the architectural point of view, what is pipelining, what is the memory hierarchy in a computing system, and like how input-output blocks look like. And then we will conclude the lectures. So feel free also to interrupt me whenever possible. Don't be shy, because I will be talking a lot, most likely during this semester. And regarding examination, we will have written exam, and also it is supported by oral exams. This semester, I will think like if I will be offering oral exam to everyone. We will see. I will make a specific announcement about that. But for now, it will, the evaluation or the examination will be composed of 2 parts: a written exam and an oral exam. Written exam will be a test. Also, we will have partial exams. I mean, it is always easier for you to join these partial exams instead of a full exam in the end of the semester. Again, this information will be given to you in more detail in the upcoming weeks, but for now, this is the structure of evaluation. Basically, a test or two tests, and also an oral exam for discussing the written exam and understanding the fact that if you really, answered questions correctly by knowing or just like by chance, we will see. And also we will have some exercises during the lectures, which will make you familiar with the questions that you will face during examinations. So in short, we will be supporting you with all information you need, with everything that will make you ready for the exams. Okay? Any questions? Anything else? If not, I continue. Basically, we have a Moodle web page. Maybe I will stop sharing here. No, not I will stop sharing. Sorry. Obviously now it is empty, but I would like everyone to enroll on this. Oh, sorry, I don't see it. Sorry. We have a Moodle page. Please enroll in this page because I will be making all announcements and I will be sharing lecture notes together with class recordings in this Moodle web page. So please, if you have not done it so far, do it because it will be very important for you to keep track of things that we are dealing with. Okay? So another. Let me just stop and okay. So Moodle web page is the main point that we will be communicating with each other. And also all the materials I will be posting there. But on the other hand, we have a very nice textbook. If you want, you would acquire it. Obviously, it's one of the best books on computer organization and design. And this is based on RISC-V architecture. It's something that even after the course, after years, you can go back and you can check the content. Of course, we don't have time to include all the chapters of this book, but after this course, maybe the ones who are interested in might proceed with the other chapters. So it's a very nice book. So this is like the conclusion. And also, we have a tutor for this class, which is Bohao. I will also announce. Oops, wait, doesn't work. You can directly reach him by also sending an email. I mean, now it is not needed, obviously, but he will be also responsible for supporting you for your questions. Also, if you have anything else to discuss, he is the first step that you will be reaching, and then I will be if still there are some problems or some issues you would like to discuss, you can directly communicate with me. So this is like basic information about the structure of the course, the content, and how we are going to evaluate. We will make all these points more and more clear in the next lectures as we progress. But so far, I think it is the basic introductory information. Anything you would like to ask? Any questions? Is it clear? If it is clear, then let's make an introduction to the computer architectures. Let's try to jump into the topic and start to discuss some very basic issues in the first introductory lecture. First, electronic computer. I mean, most likely you have heard about that, right? The history of computing started with such type of achievements. We have ENIAC, electronic numerical integrator and calculator. It is like, as you see, world's first operational electronic general purpose computer, which was built in 1946. And as you see, it is a very huge, let's say, electronic device, and it just includes 18,000 vacuum tubes. So what is a vacuum tube? It is now, I guess, obvious. I mean, not very obvious. It is something that is coming from ancient times, maybe for you, but it's one of the basic elements that does what a transistor does as we have as of now, right? So this is like something that shows how things were primitive maybe 50 years ago, 60 years ago. Now the achievement is great, right? And also, like, we have a very famous law, Moore's law. What does it say? It says that the number of transistors we can integrate onto a chip for the same cost doubles every 2 years. So what does it mean? I guess you are familiar with Moore's law, but what does it mean? What is the implication? What is like the consequence of this law? Anyone would like to comment on? So this is like an ancient computer, let's say. Now what we have is obviously significantly different, right? It's like black and white. We are now chips that have transistors inside, and it looks like the number of transistors we can integrate onto a chip doubles every 2 years. What is the implication? What does it mean? You can say yes.
The chips get faster.
The chips get faster. You are having more and more maybe computational power, right? Think like that. What you can do with 18, let's say, 18,000 transistors. Now it's like millions or more than millions, right? It looks like things are increasing even exponentially, like at some point, right? Processor transistor budgets grew quickly as microarchitectures become more complex. What does it mean? Like with more transistors, we have more complicated machines. We have more complicated architectures, computer architectures, computing architectures that offer you an enormous processing power. As you see, like when transistors started to being integrated into computers, like we had again 2,000 transistors on devices. Now, of course, this is not now. This graph shows 2011, and this is like the number of transistors that those Intel chips or some other chips, AMD, include. And now it is even, larger and bigger. You see the difference. You see the growth. You see the progress, right? So this is a kind of more recent graph that also shows that the trend is somehow something that continues, right? We are like having architectures, having electronic devices, chips, processors. Every 2 years, the number of transistors is becoming like twice more compared to the number of transistors in the past 2 years. So what does this graph shows? Like the question is like maybe in 2050 we will have the same increase, like this Moore's law still will it hold? Will it be a law that is still relevant, or there will be a discrepancy? There will be some limitations that will prevent us from integrating more transistors on chips. What is your expectation? So far, it looks like everything works, right? I mean, things are increasing. I mean, the number of transistors, which is also a metric that shows how complicated processing systems are, how powerful they are, how much processing power they can give to you. It looks like the trend is still something that holds, but will it hold? I mean, 20 years later, 50 years later, do you have any opinion on that? Yes?
No, because the transistor can't be smaller and smaller. At some point, we will be the same size. We can't possibly make it smaller.
Anything you would like to add? Yes, basically we have some physical limitations. Nowadays, engineers, designers, they are facing. You cannot make transistors smaller. At least now they are struggling with that. But maybe there will be another revolution, another finding that will enable us to still proceed with this miniaturization, I mean. But so far, so good. Things are working, let's say. Let's keep this here. You might return back to this slide later, most likely. And again, with this trend, as you see, with the advancement in the design of processing systems, like we have this, computer revolution, right? I mean, we have computing things that is spread, that is embedded everywhere. We have like computers, or let's say chips inside automobiles. We have or cell phones. They include number of processing items. We have, for example, our personal computers. We have, for example, high performance computing architectures that are designed to process enormous amount of information. For example, for Human Genome Project, a great computational power is required. For these type of projects. You need architectures, devices that gives you, enormous amount of computational power. So as you see, like from automobiles, from the devices that we carry, from large scale servers, it looks like computers are everywhere, right? And thanks to the revolution, right? This growth, this increase in the number of transistors that can be embedded inside processing architectures or inside chips. So as I said, like we have classes of computers, we have personal computers, which, as you see on the table, I have one. It enables me to do a lot of stuff. I can develop software. I can watch football matches, movies. I can do a lot of stuff, right? And we have also servers that are designed to offer some sort of computational capacity. They can be small size servers. They can be even, let's say, a building full of servers that again offers you some sort of computational power. We have supercomputers that are designed for high-end scientific and engineering calculations. For example, weather forecast is a kind of very common example of that. Again, a lot of data needs to be processed. You need to perform a lot of simulations to predict something. You need the kind of enormous computational power. And what can be another example that is more relevant today, that you need real, let's say, high computational power? AI, right? AI, artificial intelligence. You need training, right? You need to train models, for example, ChatGPT. I don't know how many days, months it requires to train a ChatGPT, a model. You have enormous amount of information that you need to fit into the model, and eventually you have something that works. What you need, clusters, a lot of let's say, not PCs, a lot of, let's say, computational elements maybe equipped with graphical processing units that will offer you that computational power, right? And we have, like, the field that I like, embedded computers. They are tiny, they are small. They can be, things that can be embedded everywhere, even wearable devices. I don't know, sensor networks, a system, let's say, that is designed to sense environment, right? Agriculture monitoring, a lot of things you can do with this type of computing elements. It looks like they are tiny, they are small, they don't offer a lot of computational power, but you can still build a lot of applications, very useful applications. You see, like, the scale from high end to low end, you have a variety of computational elements. Everything can be seen as computers, things that gives you processing power, right? I mean, This is a slide that I put. Of course, we had PCs at the beginning, right? Basically, when this computing revolution started, basically we were amazed with these personal computers that were huge. Basically, we were playing games, we were programming using these type of devices. But then there is like another revolution which is called post-PC era. It means that we started to have mobile devices. That time we didn't have, but we had tablets or things that we can carry with us. And then, as you see, at some point, smartphones popped up, and we have again computers that we can carry with us. Still very powerful, and we can do a lot of stuff with them, right? I mean, we have personal mobile devices. They are battery powered, that can be connected to internet. They are cheap. They are not very expensive. It looks like, you know, this type of achievement can be also considered as a kind of another revolution, because it is something that came after personal computers. It's called post-PC era. And also, as I was saying, like this is personal devices, mobile devices, and we have also the notion of cloud computing. I mean, we have data centers, like we have a kind of cloud that looks like a cluster of computers, like that is not a visible class. We don't know what is behind the cloud, but cloud offers us some sort of services, computational power, some sort of applications, some software services. So this is also another change in the paradigm, like from personal computers to, let's say, computers that you can carry, and also to computers that you can connect using internet, and you can get some services. You don't have the computational power, it is offered by the cloud, but you can use services maybe for free, or maybe by paying some amount of money. You can get all these services maybe in your mobile device, right? This is also a kind of change in the architecture, change in the way that we see computing systems or applications. And things are evolving nowadays. Now, like we have this AI era, like everything has AI models. Now the basic challenges to execute these models everywhere, right? So that, you know, everything becomes more and more intelligent, smart. So that is also something that changes computing architectures nowadays. But this is a basic course, so we will not be dealing with such things. We will start with fundamentals. What will you learn in this course? You will see like how programs are translated into machine language, and how hardware or how a processor executes these instructions. You will understand what is the interface between hardware and software. How does the software instruct or control the hardware to perform the functions that you would like the device to perform, right? What is performance in terms of computing architectures, how it can be improved, how can we improve the performance? You will understand it at a basic level. How hardware designers improve performance, like what are basic strategies to improve performance of a computational system, and you will also give a notion of parallel processing, right? What is parallel processing? Rather than single computational unit, you have a couple of units. You can run things simultaneously rather than sequentially. There is a kind of opportunity, if there is, obviously, it depends on the workload, to run things faster by exploiting more and more parallels. So let's say if we look, let's say at a high level, take a kind of high level point of view of the computational system, what we see, like there is an algorithm, right? There is like the software that we write. It determines the number of operations or the number of instructions or what the hardware needs to do, right? This is something that we specify as a programmer. So we have the algorithm that we implement. And then I mean, we can write this algorithm in any programming language, in C, in Python, anything we like, right? Then this algorithm is, let's say, somehow processed by the programming language or the compiler, which is dedicated to or connected to that programming language, and also architecture. We will understand what is the relationship between programming language, compiler, and architecture. And then these things, high level, let's say, description of the algorithm is translated into something that is understood, that can be understood by the underlying processing item, processing element. This determines the number of machine instructions executed for operations. So I think like that. You have a sorting algorithm, bubble sort you wrote in C, and eventually it should be translated into a set of instructions that can be executed by the computing architecture. And there's a translation. And now we have instructions that the machine understands. And then we have the processor that executes these instructions, right? And it looks like there are also additional components such as input-output devices like memory, like hard drive, or anything that you are interacting with your application. So if you are a bad programmer, you can write your algorithm, let's say, not in a very efficient way. So if you implement algorithm in a dirty way, you will not exploit the performance, right? It will run slowly, obviously, whatever you do. If the programming language or the compiler or the system software that translates that algorithm into instructions that can be understood by the machine, by the processor, let's say, if it is not generating an optimal set of instructions for the algorithm that you indicated, you will not be able to exploit the efficiency of the underlying hardware, for example, right? Or if your hardware is not good at all, if it's like a slow or like it's an inefficient architecture, then whatever you do at these two layers will not work that much because the hardware itself introduces some sort of inefficiencies, right? And if I/O system, let's say memory or these hard drive read write operations, if these are slow, these will also introduce a lot of overhead into your application, the execution of your application. So it looks like there are different layers or different, let's say, aspects that we need to consider if we want to understand the performance or if we want to improve the performance of computing systems. These things hopefully will be more clear in the end of the course. Okay? Any questions? Anything? So a couple of, let's say, high-level slides that might make sense now or that might not make sense now, but hopefully will make sense in the end of the semester. So basically in computer architectures, let's say, the idea is like to improve performance, right? To give you the best computational power. As I said, we have different levels that deals with this efficiency, performance, and how computer architecture people, let's say, design architectures for processing systems so that this efficiency, or let's say some other concerns that I will be mentioning, is handled in a kind of satisfactory way. So first of all, let's say these are like principles. Let's just check one by one. Design for Moore's law. What does it mean? It looks like if we have the trend, it looks like we will be embedding, we will be pushing more and more transistors into the architecture every 2 years. It looks like processing power will be doubled, let's say roughly. This is a kind of an obvious reality, but as I said, nowadays we are struggling with pushing more and more transistors because of physical limitations. Second, use abstractions to simplify the design. What does it mean? Like this is also not a kind of hardware-oriented idea or let's say principle, but This holds for any engineering discipline, right? I mean, if we want to solve a problem, it is better to simplify the design, not complicate it. And to be able to simplify things, we need abstractions. Also, you are familiar with those things, I guess, from your programming courses, right? Like interfaces, how to design interfaces so things become more scalable, easy to use, blah, blah, blah. These are the things that also holds for the hardware people, right? And make common case fast. So this is something that we will highlight. It looks like there are many instructions, there are many operations that is happening, that is being executed in a computing architecture. So rather than trying to optimize everything, just check what is being executed, let's say, much regularly, much frequently, and try to make that common case faster. If you do it, you will speed up things significantly. So rather than attacking all dimensions, try to just find what is like the common operation and try to optimize it rather than optimizing everything. So this is something that also makes sense, right? And as I said, we will deal with some parallelism related issues, and this is like parallelism, pipelining, prediction. Now maybe they don't make sense at all, but as I said, I will make this point clear. So these are like basic ideas that nowadays, or also not nowadays, is like basic principle to create efficient processing systems, like systems that offer great performance. And like memory, redundancy, let's skip all this for now, but let's just know that we have some principles, especially some of them are obvious in the design of computing architectures. So again, a high-level view of what is happening inside. Like, first of all, we have an application written in a high-level language, right? And then we have a system software that translates high-level algorithm software into machine code, which is called compiler. So what is machine code? Machine code is something that is understood by the underlying processing architecture, processor. So it looks like compiler should know which processor it needs to generate the code or the machine instruction. So it looks like compilers are also dependent. They are designed for specific architectures, specific computing architectures. But anyways, we have application, we have system software, which is like the compiler that translates things into the machine code. But also we might have some additional software that helps managing systems resources, such an operating system. So we don't have only our application, but we have also some low-level systems level software, such as an operating system. It manages systems resources such as memory, storage. It schedules tasks. So it looks like it is not only your program. Like you design your program, you write it, but then it should be translated into machine language. That program runs together with several applications. Maybe it is managed by an operating system. And it is not only the processor. We have also, as you see, additional hardware components like memory, like I/O. So a lot of things. Like it is not just a simple system. It's a system that interacts with many other components. So if you, again, put performance efficiency at the center of your system, it looks like there are a lot of layers, components, algorithms that needs to be taken into account, which creates a real complication. So things are not easy. So I don't know, this scene, shall I move this thing down maybe later? You can look on the left-hand side. It looks like our program code, as I always say, like the things that you write in high-level language, like a swap function, it is an abstraction, right? As you see, what we said here, use abstractions to simplify design. So what is an abstraction? if I look at this code, I don't see any hardware-oriented details, right? As a programmer, my point of view is just focus on my algorithm and implement it. That's why we have this high-level language that abstracts away all the details, hardware-oriented details, right? It creates an abstraction closer to the problem domain, and it provides productivity, portability. So I write this code, I can translate it into several other architectures. But for me, this is like something that is much more productive. I don't think these and that, a lot of other details together with my problem, which is good, right? Then there is that compiler that translates my code into an assembly language. For example, in this slide, there is RISC-V assembly language, which is understandable or not understandable. Do you understand anything? What is, for example, this SLLI? What is X6, X11? Do you have any idea? So you have abstraction, high-level algorithm implemented in C, and compiler translates it into an assembly code. And if you look at the assembly code, do we understand anything? Do you understand something? What is that SLLI? Okay, what is add? What do you see here? What is add? Sum, addition, right? What is this LD? Load, right? Load, store. So load, store, it looks like some operations for memory. Add, and a kind of arithmetic operation. So I'm looking here. What is, for example, an arithmetic operation here? Maybe k plus 1, I don't know. There are some assignments, like vk is assigned to vk plus 1, vice versa. These are variables that stay in memory. It looks like these are corresponding assembly language instructions that are generated by the compiler to execute that algorithm directly on the architecture. So it looks like it is better to write things using this, right? Not deal with all these details, but we need a compiler. Again, an abstraction, a layer that abstracts away all hardware-related details that gives you a productive and a portable application development capability. Okay, assembly language is generated by the compiler, and then there is the assembler that uses this translation and generates something that is totally ununderstandable, right? A binary machine language program, ones and zeros. The language of the computer, right? This is digital systems, binary digit. It looks like we have a hierarchy of translation when our programs are translated into things that can be understood, that can be executed by the processing architectures. So you see the abstractions here, right? The layers of computing systems here, like our application, some translation layers, compiler and assembler, and then things ready for executing at the hardware layer directly, right, by the processor. Any questions? No? I prefer you will not be that silent in upcoming lectures. I will be asking you regularly questions, by the way. But this is a lecture that I will be talking mainly. Okay. Components of a computer. Do you know what is a computer? Like, what are the basic components of a computer? Have you heard about that? I guess you have heard, but if you didn't hear about that, it is not a problem at all. That's why we have this course, right? What is a kind of basic, like let's say, just a second. Let's say we have 5 classic components forming a computing system. Obviously, we need a processor, right? Like these instructions, these binary operations should be understood and executed by a processing element, right? By a processor itself. So what is a processor? Actually, processor is composed of a data path and control. Data path and control. So these are vital components of, let's say, a computing system. And we need to have memory, right? CPU, data path and control. And there is a memory. And there should be input, output, for example, devices, because our system interacts with the user, for example, or with also with events, for example, keyboard pressing, a packet from Wi-Fi is received. Let's say all these things are things that are connected to IO devices, right? So what I would say is, like, as you see, this data path and control, which we are going to explore in the third part of these lectures, is the heart of the processor, or it's the heart of the computing system. And all others, of course, they are very important, memory, IO, but basically the instructions are executed inside the processor, which means like they are decoded, they are let's say understood by the control unit, and they are executed in the data path of the processor. Again, when you have binary instructions, these instructions are extracted, understood by the control unit. It generates the necessary signals to control the data path, and the data path performs the operations that are relevant to that instruction. For example, if you see here add is an instruction, but you see there is like a binary stream, which is like an instruction. This instruction is understood by the data path, by the control unit, and it is executed in the data path by generating necessary control signals. If this is not very clear now, it will be clear again in the upcoming lectures. Just let's create some confusion now so that you have some curiosity. Then we will answer all the questions that is needed. Okay. So, as I said, we have input-output devices. Input-output can be also some sort of user interfaces. It can be display, keyboard, mouse, anything that is connected to your computing system. So, for example, let's take a look at a device, a computing device, touch screen. So everything that can be done by using this touch screen without any keyboard or any mouse, basically, this is maybe something that was a great achievement in the past, but now it is almost nothing for us, right? So it looks like it is like, or this tablet's internal architecture. Let's just check this, disassemble it. For example, Apple iPad 2 tablet. If we look what is inside, maybe still this is a kind of old model. It looks like we have a kind of multi-touch LCD screen, which is again an IO device, input-output device, right? We have a battery here, and we have a board, which includes several components. What should be here in this board? Basically, there should be a chip or a processor, right? So what is a chip? I remember when I say chip, it is like a black box that includes, again, millions of transistors. It is something that integrates many transistors to give you some sort of processing power, processing capability. So let's also check what is inside the chip, and we have the CPU or processor. Again, as I said, what is processor? Processor is the active part of the computer. I mean, we call the overall device as computer, right? But what is inside the computer, the fundamental component, is a processor. And what I said, processor is composed of a data path and a control block. And data path is the main block that performs the computation. Also, data path, like the data is processed in the data path, that block. And control is the block that generates the necessary signals to derive the operations inside the data path. So, for example, adding numbers, checking if a number is smaller than 0 or not, multiplication, subtraction, everything is being performed in the data path inside the CPU. But data path is a stupid component, like it doesn't do things by its own. Control is the one that controls, right? Control says do addition, do multiplication on these items, for example. So they work together. Control is the one that controls it. But together they form the processor, okay? So this is what I said. Data path performs the operations on data path, right? And control generates the necessary signals to let data path perform operations. And also inside the processor, inside the CPU, we might have also a small memory, tiny memory, which we call cache memory. What is cache? Have you ever heard about that, cache? Cache memory, what is cache memory? Yes?
Is it made of stored copies of data or accessing them faster than having to retrieve them another time?
Exactly. Very good. So basically, if we have the CPU, as I said, CPU is composed of a data path and control. And we have a small memory, let's say, inside the CPU. And basically, CPU is connected to a main memory. But accessing data, reading from and writing to memory takes a lot of time. I mean, I say a lot of time, but compared to the operating or processing speed of the CPU, going through the memory, getting items, writing data is relatively slower. So rather than going through the memory, sometimes it is better to bring items into the cache memory, which is like a small memory, fast memory inside the CPU. And for example, we can reuse that data again and again without going through the memory, right? If the item is here, we can directly use the item from the cache memory rather than reading things from memory or writing things through memory. So this is what we see inside the processor: data path, control, and cache memory. So this is, again, like what do we see in Apple A5 chip? It looks like this chip also is not a single core processor. It is a dual core processor. I mean, in the previous slides, I showed you what is inside the tablet, and it looks like the chip, the main processing unit, has 2 ARM Cortex cores here. It's like it is not a single core. It has even 2 processors inside, which gives you more processing power, enables parallelism in the architecture. And we have also a GPU, graphics processing unit. As you see, it has 4 data paths. What is data path? As I said, data path is the main component that performs processing. So we have 2 processors, and on top of them, there is also a GPU, graphics processing unit, that has 4 data paths. Data path 1, 2, data path 1, 2. It looks like it has 2 graphical processing units, and each graphical processing unit has 2 data paths. It looks like, you know, I can perform processing on these 6 computational blocks. It gives you a lot of processing power. For example, you can keep maybe all these blocks busy. You can maybe use only one core, then activate two cores. It looks like, you know, this architecture is designed also to give you some sort of parallel processing power. Why do we need that? I mean, even in that simple tablet, the simple device, right? Why do we need like two cores, two CPUs, let's say, plus a graphical processing unit that has four, let's say, additional processing blocks? Why do we need that? Why do we need that level of parallelism? Or let me show you this device, a smartphone. That's a high-level presentation of the smartphone. It looks like, for example, for the camera, I have one, let's say, ARM Cortex processor, ARM Cortex core. When I say core, core also means processor, okay? You can think it like that. So for camera, I have one processor. For a sensor, for example, I have one processor. For power management, I have one processor. For Bluetooth, I have one processor. For 5G, I have one processor. For Wi-Fi, I have another processor, another chip inside this device. Why do we need this parallelism? Why not use a single processor? Or if I go back, why? 8 ideas in computer architecture. Why? One is like performance via parallelism. Any answer? No, not common case fast. This is not related with common case. Yes? Multitasking, right? There are multiple things happening in this device, right? Multiple things. I mean, there is let's say someone is calling you while you are, I don't know, maybe surfing internet or doing some stuff. And at the same time, maybe the camera was on. I don't know, like several things inherently happening simultaneously, right? And if you have one single processor, you cannot run all these operations simultaneously. So rather than one single processor distributing each task or supporting each task with dedicated processors is a better design. For scalability, for responsiveness, right? It doesn't get stuck in the middle, because when you have one single powerful processor, it will be tricky to handle things. But still, let's say rather than 10 small processors, I have one very powerful processor. I can also have one very powerful processor and I can support all these operations. Why not having one powerful processor and having, let's say, 10 tiny processors for each task? What can be a reason? Another reason, let's say, that I can put here a large, nice CPU, powerful one, and I can manage all the processing demands. Why we have 10, let's say here. Yes?
I'm not sure that, so if there is a problem with one, you have the other one.
I mean, modularity, maybe it is an acceptable answer, because, you know, if you distribute things, maybe also from the development point of view, things might be easier to manage, easier to handle. But on the other hand, it comes with additional complications. But there is another reason. Sorry? Not production cost. Maybe, I don't know, maybe it can be the reason. Yes. Abstraction, maybe. There is one very nice reason. What is that? What is this device? How is device powered? Battery, right? Rather than having a large power consuming CPU, right? You can have relatively tinier processors You can put some of them into low power mode. You can turn them off, turn them on. So power, like to save energy. Also, we are interested in power consumption of the systems. There's another angle, another dimension, which is very important. So such design also promotes it. So this is also something very important, I would like to say, especially for this type of portable systems. Okay. Normally, I give a break to have some fresh air. Today, I'm not going to give, but tomorrow, not tomorrow, Wednesday, we will have some short breaks between the lectures. Or shall I give? I don't know if you want. Shall I? Okay. Let's keep it 5 minutes at least. You know, just go out and come. So let's try to finalize the lecture. Maybe 20 minutes maximum. Okay, so silence, please. As I mentioned, abstractions. Why we have abstractions in the field of computer science, engineering? Why do we have it? To hide details, right? If we don't hide details, there are a lot of details that we need to cope with, and it makes designs or solving problems very, very difficult. So abstractions in general help us to deal with complexity. They hide low-level details so that we have, let's say, full focus on the aspects of the problem that we would like to solve. What is instruction set architecture? It is an abstraction. So it is the interface between the hardware and the software. As you see, you know, maybe I can go back to the previous slides. This one. Again, a high-level program, we have this high-level abstraction. The programming language itself gives us a kind of abstractions that makes us focus on our application, on our algorithmic problem. And for example, this is instruction set architecture. Instructions, as you see, there are some say add instruction or load, store. These are, again, abstractions. I mean, they abstract away the hardware-oriented details. They are still very low level compared to the high-level language, but still, this is the language between the computer and the software itself, right? Basically, these instructions of instruction set architecture, which is like the RISC-V. These are RISC-V instructions, right? They hide implementation details of the underlying RISC-V processor. I don't care what is happening at the level of hardware. I know that if I use this instruction, an add operation will be performed on the corresponding, let's say, data elements or registers. That the X5, X6, X10, these are registers. We will see what a register is. But as I said, ISA, instruction set architecture, is the interface between hardware and software. It encompasses, it carries all the information necessary to write a machine language program that will run correctly, including instructions, registers, memory access, blah, 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 on any RISC-V machine. I mean, for example, if I am using RISC-V instruction set architecture, instructions of RISC-V, it means that my translated program will run on any RISC-V architecture, RISC-V computer, because, again, the implementation, hardware-oriented implementation details are abstracted away, are hidden or captured by this instruction set architecture, instructions themselves. How they are implemented. Are things running fast, slow? Is it an efficient implementation of RISC-V architecture, or it's a kind of cheap one, fast one, high perform? I don't care. I write, and it will, when it is translated, it is guaranteed that it will be supported by any RISC-V machine, regardless of how things are implemented at the level of hardware. So that's why we have this abstraction provided by ISA, instruction set architecture. And there are some slides. I think at this point, this will not make that much sense because we need to cover assembly language, but also we have application binary interface. I mean, it is not only instructions that we are using, but also how our application is compatible with a kind of existing software ecosystem. For example, how parameters of a function is carried, is pushed, how registers are mapped to the parameters of function. A bit, let's say, a slide that I put here, but I know like this is not very relevant at this point. But we have also other abstractions, which is application binary interface. We will deal with that later. And apart from the processor itself, processing element itself, right? We have, as I said, I/O memory, for example, volatile memory. We have memory that maintains data, that maintains program instructions. We have non-volatile memory or secondary memory, a magnetic disk, flash memory, optical disk, solid state drive, whatever you use to store information in a kind of non-volatile permanent way, so that things do not lose, that things are not lost when there's a power failure. And I mean, using these type of memories, like, as I said, volatile memory, non-volatile memory, we can create a memory hierarchy or computing system as a memory hierarchy. For example, the main memory or the primary memory can be a volatile memory. For example, a DRAM, dynamic RAM, dynamic a memory that can be accessed in a kind of dynamic way, which means like we can store data, programs, instructions. And in the secondary memory, which it can be a non-volatile memory, it can be used to store programs permanently and to log data, to save data and other issues, for example. So we don't need to have a very large main memory, for example, DRAM, which is very expensive compared to secondary memories. We can have a memory hierarchy so that we can use it in a smart way, so that, you know, main memory can be used for program execution, secondary memory can be used for storage. So this is also a part of a computational system or for a processing system, right? We don't have only processor, we have memory, and memory is implemented as a kind of hierarchical system. We have different types of memory, main memory, secondary memory, and we decide like what will be the size, what will be the cost. Otherwise, I can give you the fastest and the best memory, and you will have a device that costs thousands of, let's say, euros or dollars, right? Also, it is important to consider the cost of the system. And I/O devices, as you know, like we can have I/O devices, or we can have, for example, devices, input-output devices for communication, so that we connect our PC to a network. We can have, for example, Wi-Fi connectivity and other stuff, or user interface, touchpads, keyboards. It looks like computing system is something that offers you processing power, but also it needs to interact with outside environment. So that's why we have also I/O blocks. So everything as a kind of whole makes a kind of processing system, processing architecture. It is not only processor, but we also need to think about how memory is organized, or how I/O or input-output related operations happen within the system. But during this course, we will be mainly focusing on processing or processor part and the memory hierarchy. We will have one single lecture about I/O, and then we will conclude our lectures. Okay, so actually I have many slides, but I'm a bit slow, talking too much. If we look at the technological trends, as I said, there is a kind of increase, or electronics technology continues to evolve. We have increased capacity and performance, processing power is increasing, and also cost is also increasing, decreasing, sorry. So we have, let's say, kind of huge processing power compared to the past devices, but things are cheaper, way cheaper now because of the technology itself. And also, if you look at, let's say, capacity of the memories, it is also not only processing power is increasing, but also memory sizes, the capacity of the memories are also increasing. Both memory, storage, and processing power, they are like following the trend, actually. So if we look, for example, at a transistor, like what is a transistor? It's just a kind of on and off switch, right? And an electronic component. Each students know it very well. Most likely, computer science students don't care what is a transistor, most likely, but it's a kind of switch, right? And like very large-scale integrated circuits consist millions of these type of switches to perform digital operations. Actually, a transistor is a kind of semiconductor device. Basically, it is like made up from silicon, right? And like from transistor to creating a VLSI chip or a processor, it's a kind of very tedious and expensive process. So, I mean, this is a high-level information, but using this some chemical processes, actually, you have a device that is conductive under specific conditions that doesn't conduct electricity. So it can be, for example, used as a kind of switch to can turn on and turn off the device, right? We are not that much interested in, but just I wanted to show you some sort of a video that gives you a high-level overview about how chips are manufactured, basically. You can watch the second video later, but let's just check this video together. Just a short video, but it is not good quality. Maybe you can check. So let's watch it and then I will explain. So as you see, like we have silicon ingots and they are sliced, and you have I think I didn't break, hopefully. So they are sliced and you have wafers. Basically, these are like the surface that, all these transistors, everything will be embedded. It is like printing process. So it is like something very sophisticated, and there are not so many companies in the world that can do such type of operations. And each single chip, billions of transistors are let's say, printed on these silicon wafers, and then you have chips that are on this, let's say, on this wafer, and you see that there are like maybe 100 chips on this wafer, and then they are tested separately, and they are, embedded, and you have your processor. I mean, this is very high level presentation. The second video is a bit more detailed. You can check it. it looks like this is something very sophisticated, and as a result of this process, you don't have all the chips working. For example, as you see, some of the chips here will not be properly working, so they are thrown away, and then they are packaged, and then you have, let's say, those chips that you can embed in any electronic system. A lot of let's say process stages needs to be exploited. So it looks like, for example, this is a wafer, 300 millimeter wafer. It includes 280 chips, 280 processors, let's say, and this 32 nanometer transistor technology, how like small, how like squeezed transistors are. And as you see, each chip, you see that each rectangle is very tiny, a kind of very sophisticated technology. It's very interesting, by the way, but it is not only electronics, it is like material science, mechanical engineering, robotics, a lot of things or expertise is required to perform such type of production. That's why there are a couple of places in the world that can do that. If you are curious about that production procedure, you can watch that video, as I said. And I think it will be, maybe I can cover a couple of more slides, then we can complete the lecture. So I was mentioning performance. What is performance? How do you describe a performance of a computing system? I mean, we will be much more satisfied, right, if our programs run faster. We don't wait. We have responses within predefined or expected amount of time. So this is something that will make us happy, right? It looks like we are interested in response time, mainly how long it takes to execute a task, or throughput. Throughput is also like how much work is done per unit time. I mean, how many transactions, how many I don't know, operations that we perform per hour, per minute. This is also a way to define the performance of systems. So we are interested in response time and throughput in general. So how these things are affected by, from which let's say, crucial aspects affect throughput and response time. For example, if we replace the processor, slower processor, with a faster version, most likely response time and throughput might decrease, right? Or if we add one more processor rather than one processor, we use two processors. Most likely, if things are parallelizable, we will finish things, much faster, right? In a shorter amount of time. It looks like parallelism is the latter, adding more processors, or speeding up the things, making the architecture faster, are two ways to improve throughput and decrease response time. So, I mean, these are not complicated things, by the way, just showing things in a bit formal way. So what is performance? We can say performance is like 1 over execution time. I mean, it is inversely proportional to the execution time. So if execution time is longer, performance is smaller. If execution time is shorter, performance is closer to 1. So it looks like we would like to have something closer to 1, right? So if we say, for example, computer X is n times faster than computer Y, what I should write, like performance of X over performance of Y, which is like, I can use this, for example, formula, 1 over execution time of X over 1 over execution time of Y. So basically they flip, and I have this execution time of Y over execution time of X. It is like, it should be n. I mean, if I say X is n times faster than Y, this is like the high level formula that I would like to use. For example, if a program, for example, takes 10 seconds on computer A, and if it takes 15 seconds on computer B, So what is like performance of X with respect to performance of Y? So what is execution time on B? It is 15. What is execution time on A? It is 10, and it is like 1.5. It looks like A is 1.5 times faster than B. Of course, you don't need to use this formula. You can also calculate things by heart, right? It is not very difficult to see. It looks like A is faster than B, obviously, right? So how much faster? 1.5 times faster than B. Clear? So actually, in a digital system, everything is executed with respect to its clock. CPU is like clocked. It is something that does its operations in response to clock cycles. So basically, like you can think like it performs, it's a very high level explanation, but an instruction, a computation at each clock cycle. So it looks like if you have a faster clock, or if you see your CPU can operate at faster frequencies, at faster clock frequencies, it looks like it's also faster. It performs operations faster. So for example, if you have a 4 gigahertz clock, it looks like you can have, let's say, you can have 4, I think this should be 4 multiplied by 10 to the power of 9 hertz. Just like you have 4 billion ticks per second. It looks like maybe you have 4 billion operations per second. Like a lot of operations can be performed, but like let's just think this clock something that does not represent actually the number of operations that have been performed, but it is a kind of good insight, like to see how fast the CPU is running. So let's just take a look at this formula. Like let's say you have some sort of operation that takes 100 clock cycles, 100 clock cycles. And if you multiply how long is one clock cycle with that number, you can understand how long it takes to execute that operation, right? I mean, you say like, okay, it takes 100 clock cycles to execute an operation, and each clock cycle is, let's say, that amount of seconds, or basically you can divide it with the clock frequency, and you can roughly estimate how much time you need to perform that operation. So if we look at this, let's say, formula, what do we see here? Like, how can we make CPU time smaller? How can we make CPU time smaller? As I said, like everything in a computing system, let's assume that is synchronized with that clock, and this clock period is a unit of time that one operation can be performed. Or let's say we will count how long it takes to perform an operation by counting how many clock periods, like how many clock cycles we need. Okay, so for example, I might be having 4 gigahertz clock or 2 gigahertz clock, whatever it is. And if my operation requires 100, let's say, CPU clock cycles, and each clock cycle, each clock pass takes, let's say, some time, picoseconds, or this is another way to represent it, like CPU clock cycles divided by the clock rate in hertz or gigahertz, let's say. This is the amount of time I need to perform my calculations, let's say 100 instructions. How is this number, how can I change this number? How can I improve the performance of the system? So what does it say? It says, first, as a programmer, let's say, I can implement my algorithm in a smarter way so that I can reduce, for example, the number of instructions or the number of clock cycles I need to perform or execute that application. It looks like I can reduce the number of clock cycles. This is on my hands, programmer. right? I can write my algorithm in a more efficient way so that when it is translated by the compiler, it is not 100 instructions, but it is 50 instructions. Maybe I have a smart way to implement my algorithm, right? This is how a programmer or an efficient programmer can do things. Is it clear? Then increasing the clock rate. I mean, maybe, okay, I cannot further optimize my program. Let's say I have 100 instructions for sure that needs to be executed. But how fast can it be executed? It is dictated by the clock rate or how fast the CPU can process things, right? So it looks like if I can increase the clock rate, or if I can make CPU run faster, obviously I can decrease the amount of time required to execute the application. So in short, hardware designer must often trade off clock rate against cycle count. What does it mean? Hardware designer can design the system, optimize the hardware so that it can work at faster speed, or in other words, you can have a faster clock signal that the hardware can operate on. This is a hardware optimization, basically. Or again, cycle count, or the number of instructions, the number of CPU clock cycles. As I said, it can be something that a programmer can play with, but also the hardware designer can also introduce some faster implementation of instructions, let's say, or some complex instructions rather than 100 instruction. Maybe you can use some hardware supported instructions that can take less number of clock cycles, but this also comes with complication at the hardware layer. Anyways, so for us, for now, I think it is better to understand two layers, what can be done. Let's say as a programmer, I can write my application more efficiently. At the hardware layer, I can design the hardware in such a way that it can run faster. So there is a trade-off. So there is like two worlds that can support each other. Okay, so I would like to stop at this point. It is enough, I guess, for the first lecture. Let's conclude. First of all, as I said, this is an introductory lecture. There are some points that might not be very clear. We will make everything clear, hopefully, in the next weeks, starting from the initial topics. Let's say this is just something that try to cover everything. Second, I think I don't know, like if it is feasible, but maybe we might be moving our classes on Wednesday. If it is okay for everyone, to Tuesday. I don't know if there are some conflicts for now. We will see. I just asked. Maybe it is not feasible. Maybe you have some conflicting lectures. But if you are also free, both computer science and HS students, we might be moving to Tuesday. Not guaranteed, but this week for sure, Wednesday we see each other. Okay.